In graph theory, breadth-first search is a strategy for searching in a graph when search is limited to essentially two operations: visit and inspect a node of a graph. Gain access to visit the nodes that neighbor the currently visited node. The BFS begins at a root node and inspects all the neighboring nodes. Then for each of those neighbor nodes in turn, it inspects their neighbor nodes which were unvisited, and so on. Compare BFS with the equivalent, but more memory-efficient iterative deepening depth-first search in contrast with depth-first search. Algorithm. The algorithm uses a queue data structure to store intermediate results as it traverses the graph, as follows: anchor the root node, declare a node and examine it. If the element sought is found in this node, quit the search and return a result. Otherwise anchor any successors that have not yet been discovered. If the queue is empty, every node on the graph has been examined. Quit the search and return not found. If the queue is not empty, repeat from step 2. Pseudocode, input, a graph G and a root V of G. 1 procedure BFS, G, V, is, 2 create a QQ, 3 create a set V, 4 add V to V, 5 anchor V onto Q, 6 while Q is not empty loop, 7 T a QDeca, 8 if T is what we are looking for then, 9 return T, 10 end if, 11 for all edges E and G adjacent edges, T, loop, 12 U a G adjacent vertex, T, E, 13 if U is not in V then, 14 add U to V, 15 anchor U onto Q, 16 end if, 17 end loop, 18 end loop, 19 return none, 20 end. BFS. Features: space complexity, when the number of vertices in the graph is known ahead of time, and additional data structures are used to determine which vertices have already been added to the queue. The space complexity can be expressed as where is the cardinality of the set of vertices. If the graph is represented by an adjacency list, it occupies space in memory, while an adjacency matrix representation occupies time complexity. The time complexity can be expressed as since every vertex and every edge will be explored in the worst case. Note, may vary between and, depending on how sparse the input graph is. Applications: breadth-first search can be used to solve many problems in graph theory, for example, finding all nodes within one connected component, copying collection, Cheney's algorithm, finding the shortest path between two nodes U and V, testing a graph for bipartiteness, reverse, Cuthill-McKee mesh numbering, Ford-Fulkerson method for computing the maximum flow in a flow network, serialization-deserialization of a binary tree versus serialization in sorted order, allows the tree to be reconstructed in an efficient manner. Construction of the failure function of the Ahu-Korosik pattern matcher. Finding connected components, the set of nodes reached by a BFS form the connected component containing the starting node. Testing bipartiteness, BFS can be used to test bipartiteness, by starting the search at any vertex and giving alternating labels to the vertices visited during the search. That is, give label 0 to the starting vertex, 1 to all its neighbors, 0 to those neighbors' neighbors, and so on. If at any step a vertex has neighbors with the same label as itself, then the graph is not bipartite. If the search ends without such a situation occurring, then the graph is bipartite. See also, depth-first search, iterative deepening depth-first search, level structure, lexicographic breadth-first search, references. External links, breadth-first explanation and example, open data structures, section 12.3.1, breadth-first search.